All right, today I'm going to focus on a problem from the interference and diffraction lesson. This was one of our big ideas for the unit, and it focuses on Young's experiment. So Young was not really a valued scientist during his day. This experiment that he did, his double slit experiment, was a huge supporter of the wave model, even though at the time no one really gave him credit for it. So what happened was, in Young's experiment, he took an apparatus with a screen. At the far end of the screen, he had a, I don't know, you could look at it as a card, and he had basically a slice in the card that we ideally look at as two slits. All right? Now, the whole point here is that if you shine light at those slits, you shine light at an opening, the light behaves as a wave, and you get diffraction. So those wave fronts come across, they hit these openings, they kind of jam up. The bigger the wavelength and the smaller the opening, the more diffraction you get. They interfere when they go through those openings, and what happens is they interfere through the openings and all the way across, and then when they hit the wall, we get these bright and dark spots as a result of the interference. Now remember, the bright spots where you'd see like the light, you remember we did it with the laser, those bright spots are constructive interference. That is where the difference in path between the two sources is an exact one wavelength integer multiple. And what I mean by that is, remember there's always a path difference. So let's say that this is a bright spot on the wall right here. If you take the one wave, and this is just an idealized version, and the other wave, there's a path difference. The bottom one has to go a further distance. So if this difference in distance here, which I'm not going to go through here, but if you look at the math in the text or from the notes, if this difference in path is exactly one wavelength or exactly two or exactly three wavelengths, this one is caught up. So the waves end up meeting in exact unison, in phase here. They build constructively and you get a bright spot. If one of the waves is exactly a half wavelength behind or a half wavelength ahead, you get destructive interference. So remember that this path difference is going to determine where on the wall I get bright spots and where on the wall I get dark spots. Okay? So coming to this problem at hand here, that's built off of Young's experiment, it says when 546 nanometer light passes through a particular diffraction grating, a second order principal maximum is observed at an angle of 16 degrees. From there, how many lines per centimeter does the grating have? Well, I'm going to erase this for the time being and just look at the specific problem. I've drawn a little diffraction grating up here. The diffraction grating problems are very similar to the ones with the slit. All a diffraction grating is thousands of slits. So we kind of look at the problem the same way, just with several thousand slits instead of one. The little distance here between slits was d in our formula. Okay, so we're focusing on the math here, but we're going to come back to the theory. So the first question would be is asking us to find the distance between the slits, basically, because to find the number of lines per centimeter, we're going to go about this in a three-step process. One, I'm going to find the distance between the slits. Two, I'm going to take the inverse of that number, because 1 over d is the diffraction grating ruling. So like if I find the distance between slits, if I go 1 over that number, I get the number of lines total. And then once I've done that, I'm just going to convert it into centimeters, because the question asks for lines per centimeter. Okay? So first, when this light comes through, it's going to create a diffraction pattern. I keep telling you guys it's unfortunate I can't show bright fringes on a board, so I'm just going to make a mark here that's supposed to be the central bright fringe. That's called the central maximum. It's at n equals 0. It's the brightest of the fringes. Remember, all the fringes are the same distance apart. We then have another bright fringe at n equals 1. This would be the next bright fringe you would see from the central one. And then up here would be n equals 2. They're all equally spaced apart. There would be an n equals 1 below and an n equals 2 below. Okay? So that's the pattern we're going to get. In the question, we're looking at we're looking at the second order principal maximum. Be careful. If it's asking for a dark spot, we're looking for like a node or a minimum where it's destructive. This is constructive interference. It's a bright spot. We're looking up to here, okay? Now we're given the angle up to that spot. This is called the angle of diffraction. This was 16 degrees. And we're going to use, I mean, you have a choice of formula, usually. Be careful here, you see how it's 16 degrees? We cannot use the other formula, the approximation formula here, because it's over 10 degrees. I'm going to use, first, lambda is equal to d sine theta over n. And what I'm doing here, this is to find the distance between the slits. I'm looking for d. So if I plug in what I know the wavelength of the light is 546 nanometers. I'm looking for d, and I know the sine of the angle is 16 degrees. In the bottom, n is 2. All right, this is just the formula. This is on your formula sheet. And then from here, I'm going to solve for d. D comes out to 3.9617 times 10 to the negative 6 meters. Okay? And next, if I found that value, which is the distance between slits, I can find the number of lines per meter by taking the inverse of that. So if I go 1 over d, 1 over d is going to be equal to the number of lines in my diffraction ruling. So I'm going to go 1 over this, and I get 252,415 lines. Okay? So that's how many lines there are in the diffraction ruling. From here, now I just need to convert that to centimeters, okay? So quick recap, I found d, the distance between slits, which I then took the inverse of. I now know how many thousands of lines I have in my diffraction ruling. Problem is this is in lines per meter. So I have this many lines per meter. I want to know how many lines I have per centimeter, so I'm going to do a quick ratio. I'm just going to set up a ratio on both sides. On the left-hand side of my ratio, I'm going to have the 252,415 lines in 1 meter. And I want to know how many I have in 1 centimeter. So on the other hand side, I'm going to have x lines, my unknown, over, well, 1 centimeter is 0.01 meters, so I'm going to put 0.01 here, because it's for 1 centimeter, which is a hundredth of a meter. So if you solve that expression there, the proportion, you'll find that there are 2,524 lines in a centimeter. Okay, and that answers the first part of the question. That makes sense, right? You should have more lines in a full meter than you would in a full centimeter, right? There'd only be this many lines in a centimeter. The further you go, the more total lines you have to get to a meter. Next, the question's asking in B, what would happen if we changed the wavelength of the light? So what if we use longer wavelength light? Well, assuming the distance between the slits stays the same, so our opening that we're getting diffraction on, assuming that stays the same, a longer wavelength is going to mean more diffraction. Okay, so I know that this is going to result in more diffraction, meaning the spacing between the fringes gets further apart. But in general, when you're asked, how does one variable affect another, you want to go find the formula on your formula sheet that deals with the relationship and look at that. So for B, I would look at the fact that if you go to this formula, I'm just going to write it here, lambda equals d sine theta over n. If you go look at the variables there, lambda is directly proportional to sine theta, where that is the angle of diffraction. So if the wavelength increases, sine theta has to increase as well. So that means that these angles are getting bigger for each fringe. Bigger angles mean that they're more widely spaced. Okay? Now C is asking, I'm just going to erase this here. to make some room. C is asking, all right, if it's 1.5 meters away, what is the distance from the central maximum to the second order maximum? So basically, the distance from n equals 0 to n equals 2. Again, be careful if we're using destructive, if we're looking for nodes or destructive interference, it's going to be up to like a half multiple. But here we're going up to n equals 2. We cannot use the formula lambda equals dx over nl. It would be nice, but we can't. It's an approximation, that formula, and we're over 10 degrees, so we cannot use that. Here what we can do is we can use simple trig, if you've drawn the diagram. And diagrams are great. Use diagrams whenever you can. If you look at this, we've got a right angled triangle set up here. So if you look at theta, we're looking for this side here, basically the triangle. So we can use tan, opposite over adjacent. So if you go tan 16 degrees, that's the opposite side, which we can call x, over the adjacent side, which is 1.5. Okay? And if you solve this, you get that the distance is 0.43 meters. Okay? So 0.43 meters from here to here.